Welcome to our post-lunch session on key exchange and messaging. We'll be starting it out with Xiangyu Liu telling us about EKE meets tight security in the universally composable framework. Take it away.
Okay, can you hear me? Okay, it works. Well, thank you for your introduction. And I'm Xiangyu Liu from Purdue University, and the title is EKE meets tight security in the universally composable framework. It's a joint work with Shengli Liu, Shuai Han, and Dawu Gu in Shanghai Jiaotong University. Well, we may start from PKC, password-based authenticated key exchange protocol, as shown in this figure. The involved two parties, usually the client and the server, they pre-shared a short password PW, and after several rounds of interaction, they finally output the same and pseudo-random session key KC or KS. Usually, this password is short and is human remember. And besides, the entropy of the password is very limited. Different from AKE, in PKE, we do not need complicated cryptographic keys for signatures or for encryptions. Well, PKE has an asymmetric variant, which we call the APK. In APK, differently, the server now stores a password field rather than the password in plain. Usually, the password field is a hash value of password, and APK is designed to prevent potential attacks. For example, the adversary may log in the server and steal the password field. So in APK, we required even with the password field, the adversary cannot impersonate a client to log into a server. Well, we consider the UC framework, UC security in this work, and we may tell something about UC framework, universally composable framework. And this, the left figure shows the real world view, and the right figure shows the ideal world view. We say protocol is UC secure if it emulates some ideal functionality F, so that the real world view is indistinguishable from the ideal world view. And compared to indistinguishability, ND-based security model, UC security model has several advantages. For example, it supports arbitrary correlation and distribution for password, and the universal composition theory is applicable. That means the security of the protocol preserves even it's running in arbitrary networks where multiple protocol instances may run in parallel. Well, in this work, we also consider tight security. So we may tell something about reduction. We know in proof of security, we designed a protocol or a scheme as based on some problem P, and we make a reduction to prove the security. In the reduction, we define security loss factor as L over epsilon over epsilon prime, where epsilon is the advantager of the adversary A, and epsilon prime is the advantager of the reduction algorithm B. From the definition, we can see, obviously, the smaller the security loss factor is, the better. And tight security means L is a constant, or L is a polynomial in lambda, the security parameter. And in contrast, loose security means L depends on A's behaviors. For example, depends on the number of users or sessions involved by the adversary A. By standard hybrid argument, we know security in the single users and single session setting implies security in the multi-user and multi-session setting, but with a cost of huge security loss. Usually, this cost can be as high as 2 to 30 to 2 to 50. So that's why we try to design tightly secure cryptographic schemes, since tight security has many advantages. For example, universal parameters and the smaller parameters under the same security level. Okay. Now, in terms of tightly secure PKE and APKE schemes, there are only two related works. The first one, BIO plus 17, it proposed PKE protocol based on gap DH assumption in the ND model. We already mentioned that the ND model is weaker than the UC model. And the other work, ABB plus 20, it's proposed a tightly secure PKE protocol also based on the gap DH assumption in the relaxed UC model. Here, gap DH assumption states that given G, G2X, G2Y, as well as the decision oracle for DDH tuples, it's still hard to compute G2XY. Since it involves a decision oracle and is interactive, so we may sometimes, to some extent, consider it as non-standard. So in this work, we aim to design a PKE protocol as well as an APK protocol with tight security in the standard UC framework, probably from standard harness assumption like the CDH assumption. So that's our goal. And we make the following contributions. First, we proposed twin DH EKE. It's a PKE protocol, and we prove its tight UC security based on the CDH assumption. We also want to extend it to the asymmetric version, but we found a negative result. That is, APKE protocols cannot achieve full tight security. And the security loss factor is lower bounded by n, the total number of client server pairs. Nevertheless, we still propose the twin DH AEKE. It's an APKE protocol, and we prove its UC security based on the CDH assumption, and the security loss factor is, that it means the optimal security loss. So now we may tell some technical details, and we may start from EKE protocol. Encrypted key exchange protocol is proposed by Blevin and Metric in 1992, and I think it's the first, also the most well-known PKE protocol of the world. As shown in this figure, it's rather simple. In high level, it just encrypts every transcript message for a regular key exchange protocol. Now, for example, the client is samples GX and encrypt G2X using password as the symmetric key to obtain the E1 and send this out. And the servers do similarly. The final session key is computed as H trans Z, which is equal to G2XY. And trans may include the transcript information as well as some public information like the identities of involved parties. Now, we want to prove the tight security of EKE. That is, we want to make a reduction, and the reduction algorithm B intuitively it's first need to randomize the CDH or DDH challenge problem and embed them into multiple session instances. And this due to the random self-reducibility of the DH problem. But we may face the two following obstacles. First, if now suppose the adversary A attacks successfully, for example, is all powerful and it can compute the CDH problem. So that means it can compute the real session key. But in this case, B has already embedded the challenge problem into these sessions. That means B can not compute the session key as A. But if A attacks successfully, how can B extract the correct CDH value from the hash list? Since there might be thousands candidates Z in the hash list, and B does not know which one is correct. So that's the first obstacle. And for the second obstacle, now if A correctly gets the password, so how can B do? Since in this case B cannot compute the session key as before, and we notice that since the password entropy is very limited, that means A can guess it correctly with a non-negligible probability. So in this case, how can we do? So we need on the way towards tight security, we need to solve these two obstacles. And our idea is to resort to a decision oracle. We noticed that in 2008, Cash, Qs, and Shrew, they proposed the strong twin-DH assumption, and Schultz proves its equivalent to the standard CDH assumption. Here, strong twin-DH assumption states that given G to X1, G to X2, and G to Y, as well as a decision oracle twin-DH, it's still hard to compute G to X1Y and G to X2Y. Here, twin-DH is a decision oracle that it inputs G to Y prime, G to Z1, and G to Z2, and it outputs whether X1Y prime is equal to Z1 and X2Y prime is equal to Z2. So knowing the strong twin-DH assumption, we now design twin-DH EKE protocol as follows. Now, the client samples X1 and X2 and encrypts G to X1 as well as G to X2 using password as a symmetric key and obtains Z1 and sends it out. The server does similarly. It samples Y and encrypts G to Y to obtain E2. And now the session key is computed as hash chance Z1 and Z2, where Z1 is equal to G to X1Y and Z2 is equal to G to X2Y. And the security of twin-DH EKE is based on the strong twin-DH assumption, which is equivalent to the standard CDH assumption. Now, let's have a look why twin-DH EKE can miss tight security. That is, we need to solve the two obstacles we mentioned above. And for the first obstacle, now, since in the reduction algorithm B, it can locate the correct CDH values Z1 and Z2 by checking twin-DH Y, Z1, Z2 is equal to Y. So it can locate the correct values and solve the challenge problem exactly. And for the second obstacle, if A gets the password correctly, now in the reduction, B just samples a random key and view it as the real session key and return it to the adversary A. And if A later adds a hash, which works as a random oracle with the correct value, then B can notice it, and it's just reprogram the random oracle to make A's view be consistent. And this can be done due to the simulation of random oracle as well as the twin-DH assumption, as well as the twin-DH decision oracle. So we solve the two obstacles, and that means twin-DH EKE means tight security. Well, we also consider UC security in our protocol, and that's done by ideal ciphers. Actually, in twin-DH EKE, we modeled the symmetric encryption schemes E1 and E2 as ideal ciphers. That means we can simulate transcripts E1 and E2 without knowing passwords. Also, we can deduce the password gaze PW prime in the adversary's mind from the ideal cipher list. And if the gaze is correct, we just execute the protocol honestly and return the real session key. And if the gaze is wrong, we just return a random key, and the security rely on strong twin-DH assumption, which is equivalent to the standard CDH assumption. Now, for the last step, we extend it to the asymmetric variant. Namely, we design twin-DH AEKE protocol, and it has two main differences. First, we need to add additional computation steps, which is highlighted in blue. Now, in the computation of session keys, we need to add Z3, Z4 in the hash input, where Z3 is equal to G V1Y and Z4 is equal to G V2Y. That's the first difference. And for the second main difference, we add a MAC sigma from the client to the server to achieve perfect forward security. And we prove the we prove the UC security of 20H AEKE based on the strong 20H assumption, and the security loss is in this work, we finally prove that for APAKE, simple reductions have an optimal security loss and the total number of client server pairs. Here, simple reduction means in the reduction algorithm just invokes the adversary A only once. Almost all known proof techniques fall into this type of simple reduction. That means 20H AEKE means optimal security loss. Okay, to make a conclusion, in this work, we proposed the 20H EKE protocol and show its tight UC security based on the CDH assumption. And we also gave a negative result for the tight security of AEKE, and design 20H AEKE shows its optimal security loss. That's the main idea of this work, and thank you for your attention.
We have time for questions if anyone has a question.
Do you have some insight into what aspect of APAC as compared to PAIC makes it so that you can't achieve better than this factor N security loss?
You mean the difference between PAC and APAC?
Yeah, what about it makes it harder to have a tight security? Projection?
Okay. We can show in this figure. We can see the password field. It works as, we can view it as a commitment from the client to the server. And to achieve tight security in the reduction, we do not know whether the adversary can obtain the original password from the password field, since it can guess, and it can check whether the guess is correct since it's known the password field. So due to this reason, we do not know where and when will the adversary successfully obtain the original password. And if it does, then the security is break. So due to this reason, we have to choose one particular session and embed the hard problem into it. That leads to the loose security loss factor. And
that makes sense. Thank you.
Thank you.
And no other questions. I have one. So
Yes.
Part of your motivation for studying tightness was it's nice when you do a hybrid argument from single user to multi-user. With this security loss of N, were you able to do just a proof for a single pair and then do a hybrid, or did your analysis really need to analyze all?
Well, if we use hybrid arguments, we have not only the loss factor N, but also maybe Q, where Q depends on the session in total number of hash queries involved by A. But so N times Q is usually larger than N. So the security loss N makes sense.
Let's thank our speaker again.
Thank you.
Next up, we'll have paper 170. And while I'm talking to y'all, we have our aquarium visit today. We're going to have 2 bus trips, one at 5:30, one at 6 o'clock. Okay. And so this talk is going to be on a universally composable PAIC with 0 communication cost and why it shouldn't be considered UC secure. And the talk will be given by Lawrence Roy. Take it away.
Hear me? Yes, okay. Hello, everyone. I'd like to present Jayu and my analysis of correctness in universally composable password authenticated key exchange. So as usual, Alice and Bob want to find a shared symmetric key that they can use to communicate. So they use Diffie-Hellman key exchange. Over an authenticated channel, this works great. the adversary is just an eavesdropper and cannot find the key without solving the Diffie-Hellman problem. However, it falls apart against a man-in-the-middle adversary. That is, if the parties communicate over an unauthenticated channel, then the adversary can replace their messages with its own, and completing a separate key exchange of each party. So Alice and Bob now think they share a key, when really each shares a key with the adversary. So let's say that Alice and Bob now share a secret password, which might be of low entropy, like many passwords are in practice. With a password authenticated key exchange, or PAKE, they can use this password to stop a man-in-the-middle attack. So PAKE is illustrated here as the encrypted key exchange protocol that you just heard about in the last talk, which encrypts Diffie-Hellman key messages with an ideal cipher, using the password as a key. When not under attack, the parties can successfully decrypt each of those messages and then agree on a key the same as Diffie-Hellman. And now let's say there's a man-in-the-middle adversary. The adversary now has a choice. It can either leave Alice's message A unchanged, but then it won't learn Bob's key because effectively it becomes just a Diffie-Hellman key exchange again. Alternatively, it can modify Alice's message to get A prime, but this requires guessing which password to encrypt under. And then guesses wrong, the message will be decrypted to a random Diffie-Hellman group element, and again, it becomes a random key that the adversary can't guess. So this gives them an intuition as to like the sort of security properties that PAKE provides. The full security properties are defined, have been defined in two ways. One is the game-based model, and the other is in the universal composability framework. And the UC definition has since become standard. So by far the most commonly used for PAKE. So now I'll present our trivial PAKE. Here, Alice and Bob send no messages and instead just sample their own keys uniformly at random. So the question is this a PAKE? Like, I mean, obviously not, as it's not correct, right? This is like, in the so-called key exchange protocol, the only way the two parties can agree on a key is by accident. But actually, it does satisfy the UC ideal functionality for a PAKE. To see why, we need to look at the UC PAKE ideal functionality of Canetti et al. So the key features of this ideal functionality are test password and new key. So the simulator can use test password to test a password guess against a fresh session. If the simulator guesses correctly, then the session will become compromised and the simulator be told that their guess is correct. Similarly, if the guess is wrong, they'll be told their guess is wrong. But this time the session will be interrupted. Later on, when the simulator submits a new key query to tell the functionality to output a key to a given party, what key's output depends on the state of the session. So if it's compromised, the simulator gets to choose which key to output to that party. If it's interrupted, then it's just going to get a random key. The party is just going to get a random key. And only when the session is fresh, that is like is neither corrupted nor interrupted, will the functionality like do what you'd expect the PAKE to do in like the honest case where it generates a random key and gives the same key to both parties. Now, to show that the trivial PAKE implements the PAKE ideal functionality, we need to show a simulator that makes the ideal world here match the real world. So in particular, the simulator needs to make the ideal functionality also output independent uniformly random keys to the two parties. So to do this, we just have the simulator interrupt both sessions. That is, the simulator will pick a fake password. Oops. The simulator will pick a fake password, here just written as bot, that neither party will use, either like randomly or as some sentinel value, I guess. And then try guessing this password against both parties. Since the guess is they're always going to guess wrong, both sessions get interrupted, So then when you can just provide any key you want to new key, this key will get ignored. And the new key query will just send a new fresh uniformly random key to both Alice and Bob here. But actually, there's an even simpler example of a trivial opaque. If you do nothing and never output a key, so the protocol never completes. So is this opaque now? Well, it also satisfies the ideal functionality. Why? Well, recall that the opaque ideal functionality only outputs a key when the simulator sends the new key query. The simulator can just decide to never send new key, and then the simulation will be perfect because the ideal functionality is never going to send a key. So I should note that this empty pake was already pointed out by Kennedy et al. In the original UC pake paper. One of the results is a proof that pake is impossible in the plane model. But the thing is, this empty pake works in the plane model. So to resolve this, they need to have an additional condition on the proof, which is that the pake is non-trivial. So as you can see, yeah, they have a non-trivial requirement motivated by this empty pake protocol. However, the existence of the empty pake protocol is more of a general problem. It's not really very specific to pake at all. Because it's also true of authenticated key exchange or two-party computation or other things as well. That is, it's just because UC usually works in a asynchronous model, letting the adversary delay protocol execution arbitrarily. And if the adversary can decide to never deliver any messages at all, then every protocol kind of looks like this. So because this is a generic issue, it's not as relevant to our focus on pake. And so I'll mostly skip past this particular problem for this presentation. So we analyzed several ways of fixing the pake definition to include correctness. So while we showed they're all equivalent, that doesn't necessarily mean that they're all equally useful. Some might be more convenient to use for some purpose. So the first approach is the simplest. You can just explicitly require that the protocol is correct. That's what the non-triviality condition of Kennedy et al. Did. For their impossibility proof. I mean, also it seems like a pretty reasonable thing to do. Like most game-based definitions will have a security property and a correctness property, and they're separate things. But UC tends to work differently. If UC, usually the whole definition is given by the ideal functionality. And that's very important for composition because any protocol that's built using pake will be defined or analyzed in the pake hybrid model. So you won't be analyzing it using some concrete pake. You'll be analyzing it as using this pake ideal functionality, and then use the composition theorem to show that it works when you instantiate it a concrete pake. Now, if this pake ideal functionality doesn't guarantee correctness, whatever protocol you're building on top is not going to be able to. You're not going to be able to analyze it assuming correctness holds in the hybrid model, because it doesn't hold in the hybrid model. So next we tried to look at more of the underlying reason for this problem. So it seems like the pake ideal functionality is giving the simulator too much power. Intuitively, is the test password query corresponds to the adversary replacing an honest party's message with their own message. If they replace a message, then they can put their own password guess into this message. So this suggests another approach, restricting to reasonable simulators, meaning simulators that only use test password when the adversary decides to tamper with a message. So there's a number of ways you could define this. So for a reasonable, one way is the reasonable simulator. So, excuse me. One way is a reasonable simulator. So if the adversary is an eavesdropper, meaning it doesn't modify any messages, it just eavesdrops. And then the simulator must not use test password except with negligible probability. Next is a strong reasonable simulator, which is a bit more a slightly stronger notion. At least it looks like it's slightly stronger initially. So it's additionally required to requires the simulator to not call test password before A modifies a message, even if A is going to later modify a message. So even if A is not an eavesdropper, as long as A behaves like an eavesdropper, then it will the simulator must still not call test password. And then finally, there's a couple other tweaks you can make, like probability 1 instead of negligible probability, or maybe some more interesting one is to require that all successful simulators, meaning all simulators that can be used to prove that the protocol instantiates the ideal functionality, satisfy one of these reasonability definitions. So it turns out these last two things are incompatible. So it's always possible to construct simulators that violate reasonable or strongly reasonable with non-zero but negligible probability. So that means we can't say that all successful simulators are perfectly reasonable, for example. But if we exclude this one compatibility, it turns out all combinations of these like ways of defining it are equivalent. We proved this in our paper. However, ideally, we would like to make it work with just the ideal functionality. We'd like to fix that works with just UC with no outside requirements on the protocol or the simulator, and then everything would work nicely with the composition theorem. Unfortunately, we proved this is impossible to fix just by changing the ideal functionality alone. The ideal functionality has no way to tell whether the adversary is acting as an eavesdropper or a man in the middle. In the latter case, the adversary can corrupt the protocol messages, so the simulator needs the power to make the PAKE output independently random keys. So yeah, it needs to be able to output independently random keys if it's a man in the middle. But if it's the eavesdropper, we need to not give the simulator this power, because otherwise the simulator can use that power to make the trivial PAKE a PAKE. So we have this problem is like the ideal functionality just doesn't have enough information to model it properly. So this suggests that maybe we need to change things up a little bit. We need to change something so that the ideal functionality can know whether the adversary is behaving as an eavesdropper or a man in the middle. So we revisited the unauthenticated channel model that the PAKEs are built in. So when Alice and Bob are communicating over an unauthenticated channel, this really means that they're just talking directly to the adversary. It only really functions as a channel if the adversary decides to send the messages back and forth. So it's only at the will of the adversary that's the channel. So maybe a slightly more realistic model is that Alice and Bob are talking to each other over some untrusted network, illustrated as a router here. And when the router is working properly, the adversary can only eavesdrop on the messages passing through. It cannot actually change the messages. But if the adversary corrupts the router, then it can modify the messages arbitrarily, as with the unauthenticated channel. So to model this, we treat the router as a third party in the protocol, PAKE protocol, and give Alice and Bob authenticated channels to communicate with the router. So we also require that the uncorrupted router its job is only to pass messages. It can't do any like actual computation. So the protocol doesn't get to specify what the router does. That's predefined. But if the router is corrupted, then the adversary gets to tell the router to do whatever it wants, and then it gets to modify the messages, and just like if it corrupts any other party. So with this model, we only needed to slightly tweak the PAKE ideal functionality to include correctness. PAKE where we just need to make test password queries come from a corrupted party instead of from the simulator. And that way, if nobody's corrupted, the simulator can't use test password to interrupt the session. And so the trivial PAKE doesn't satisfy the definition. In fact, we proved that that satisfying this definition is equivalent to satisfying the original UC PAKE definition and also satisfying correctness. And it also turns out that each of these approaches to requiring correctness also has a natural corresponding approach to requiring the protocol to output a key to rule out the empty PAKE. So if we require correctness as a separate property, we might as well require the protocol complete as a separate property. For reasonable simulators, we can require the simulator to eventually send the new key messages if the adversary eventually delivers all of its messages. All the messages in the real world, the adversary eventually delivers messages. And for the three-party PAKE model, it's a bit more complicated, but it is possible to fix it using a technique from a paper by Katz et al. That shows how to model synchronous computation in UC. All right, and in conclusion, we presented a UC PAKE that does not satisfy correctness. While we focused on PAKE, similar issues can occur in other protocols that work over unauthenticated channels. For example, UC notions of authenticated key exchange also fail to guarantee correctness in this way. We analyzed several approaches to fixing the definition to include correctness, which turned out to be equivalent. First was to explicitly require the protocol to be correct. Second was to nerf the simulator, so it cannot use test password when the adversary is just an eavesdropper. Unfortunately showed that it cannot be fixed just by changing the ideal functionality, but we can fix it if we add the router as a third party and tweak the ideal functionality slightly. This gives a composable PAKE definition that includes correctness, allowing higher level protocols to be built on top of this PAKE hybrid model while being able to assume correctness inside those protocols. And similar approaches work to rule out the empty PAKE as well. Thank you.
We have time for questions.
Does the definition problem occurs in some other UC frameworks, for example, for AKE and some other protocols?
AKE, yes. I
It
think
means it has the same problem,
yes.
right? Oh,
I think it's probably generic to a lot of like unauthenticated key exchange, unauthenticated channel protocols, but authenticated key exchange is the only other one we've looked at. So.
okay. Due to they do not consider correctness. Okay, thank you.
So you said you had a couple of different ways of kind of fixing this,
Mhm.
you know, maybe 3 or so. Do you have any recommendation for somebody writing a random paper, which of the 3 formalisms they should use?
I mean, one answer is whatever makes your proof easiest, since they're equivalent. But I like the 3-party PAKE version the best. I like how it fits with the composition model. I think that's probably easiest if you're using a PAKE. If you're creating it, if you're trying to prove something is a PAKE, I think the reasonable simulators definition may actually be the most convenient.
Thank you very much. Let's thank our speaker again. Next up will be paper number 2. Well, this paper will be moving away from PAKEs and talking about key encapsulation, in particular, sender binding key encapsulation. Our speaker will be Vasilij.
Test. So I'm going to cheat a little bit. I hope that's okay. So my name is Vasily Beskorovainov, and I'm going to present results from our joint work with Lauren Benz, Vasily Beskorovainov, Sarai Albrecht, Jon Müller-Quade, and Astrid Ottenhuis. While most of the co-authors are from the well-known University of KIT, me and Sarai Albrecht are from a small research institute, FZI, located also in Karlsruhe. First of all, I would like to motivate the concept of a secure channel. The basic intuition of such a strong channel is that an adversary is not allowed to learn anything except that there is communication taking place. Employing only CCA2 secure encryption, however, is not enough. The adversary may relay the honest ciphertext to another party in the name of a controlled party or a corrupted party, which is going to look like an honest ciphertext from this corrupted party. With CCA2 security alone, this attack cannot be countered. However, sending such encryptions over an authenticated channel thwarts these kinds of attacks and may realize a secure channel. Please note that already here it is required that the encrypted message, the plain text, is concatenated by some form of sender identity or any other binding to the authenticated channel. So how are authenticated channels constructed? For this presentation, it's sufficient to know that an existential unforgeable chosen message attack secure signature plus some secure certification authority is enough. Just think about it as some form of sign encryption constructed in form of encrypt then sign. Now, CCA security is quite strong, as flipping a single bit of the ciphertext will be detected and rejected. Thus, CCA2 security guarantees non-malleability of the ciphertext. Adding EUF CMA signatures, however, among other things, guarantees also that manipulations of the ciphertext are going to be detected. It seems, therefore, that the integrity protection guarantees of CCA2 security and the EUF CMA security overlap. The first such observation was done by Canetti, Kravchuk, and Nielsen in the year 2003, albeit their main motivation was somewhat different. The authors proposed a relaxation of CCA2 that allows a special form of benign malleability of the ciphertext. Basically, the bit flipping example. And they introduced the replayable CCA security, which they also showed to be sufficient to realize a secure channel when combined with authenticated channels. Then McKinsey, Reiter, and Young, motivated by this exact observation, introduced a special kind of PKE, namely the tag-based PKE. Together with a further relaxation of the non-malleability intuition, namely the weak non-malleability, which basically lets the adversary manipulate everything as long as the tag inside the ciphertext is not concerned. They showed this to be sufficient for a secure channel in conjunction with authenticated channels. Both security definitions are somewhat incomparable, as RCCA and weak non-malleability concern different kind of PKE notions, and this is going to be a similar problem with sender binding CAMs and general purpose CAMs. Recently, we have introduced a more relaxed security definition than the previous tag-based weak CCA security definitions, namely sender binding CPA for sender binding encryption, and showed that this relaxed definition is still sufficient and in fact weaker than previous notions. However, in the reality, no one is going to use a solely based PKE based encryption because of the very elegant alternative by hybrid encryption. Therefore, we have asked ourselves how our relaxation of a special kind of PKE translates to the security requirements of the CAM-DEM compositions, and we have found interesting insights. The literature around hybrid encryption has produced quite a lot of works regarding the relaxation of the security requirements of the DEM or the CAM. Relaxations of the DEM included slight relaxations like indistinguishability one-time CCA, or the quite impressive results with the extremely weak security requirements of just the indistinguishability one-time security of a DEM, where the adversary does not get any access to any oracles. Last but not least, these DEM relaxations unsurprisingly require the CAM part to be CCA2 secure. For the sake of completeness, it should be mentioned that much work has been done on relaxing the CAM part and hybrid construction. Unfortunately, these relaxations miss our motivation due to the main goal of these works being a CCA2 secure hybrid PKE. In addition, they consider only the single message transfer scenario where the symmetric key is used only once, which effectively excludes a wide range of real-world applications as SSL, IPsec, and SSH. There is, however, one work by Nagao, Manabe, and Okamoto that has extended the classic single message scenario for hybrid encryption towards the session communication scenario, where the symmetric key is used multiple times throughout one session, such that the KEM part serves, well, essentially the key exchange purpose. This result enabled the usefulness of hybrid encryption in the protocols of SSL, IPsec, and SSH. However, one of their theorems is surprisingly strong. The authors use a CAM functionality that is equivalent to a CCA2 secure CAM. Thus, we have also asked ourselves whether the CCA2 CAM security is a necessary condition for a secure channel in a session communication scenario, which brings us to our contribution. First of all, we introduce yet another reformulation of a CAM, namely a sender binding CAM. In a similar fashion, we have reformulated a PKE to a sender binding encryption scheme. Also, we introduce an according security definition of SBCPA for an SB CAM. These definitions allow us to prove two important theorems. We were able to show that the previous results for SBA are also achievable by hybrid encryption when an SBCPA secure SB CAM together with an int OT DEM is used, which basically constructs an SBCPA sender binding encryption. The UC realization of secure message transfer then follows from the previous SBCPA results. The scenario of session communication is, however, somewhat more involved. We show that the same also holds here with an expected requirement that CCA2 or RCCA symmetric encryption has to be used because of the repeated usage of the exchange symmetric key in contrast to the single-use symmetric key and OTDEM security in the single message secure message transfer scenario. The interesting part here is that the authenticated channel is only required during the initial exchange of the symmetric key and not when later on communicating over the CCA2 or RCCA secure DEM. The reason is that the exchange symmetric key is used to implicitly authenticate both the sender and the receiving party. Our results can be seen as a generalization of and relaxation of the theorems from Nagao, Manabe, and Okamoto. So what is the intuition behind int-SB CPA security for a CAM? We do not care about any manipulations of the ciphertext as long as they do not concern, as long as they do concern the sender identity inside the ciphertext. Obviously, there is nothing that prevents the adversary from honestly generating encrypting a ciphertext with any known sender identity, as they are just public identities. However, keep in mind that this security is meant to be used in conjunctions with authenticated channels, and the identities are required to be bound to these channels such that an honestly generated ciphertext is also required to be sent over the according authenticated channel, which is only possible when the respective sender party is corrupted and thus is part of the adversary. Therefore, we just reject the such honest encryptions inside the SBCPA game. Now, regarding the exact formulation of the SBCPA security. The previous intuition can be found inside the formulation of the decryption oracle. Another three important details that may stand out are Instead of generating only one key pair, the challenger generates two key pairs for sender and receiver, and the adversary is handed over both public keys with their respective identities. Secondly, we have only one oracle phase, which stems from the simple fact that technically the game can be written with two oracles. Oracle phases, as usually is the case, but both phases are, in contrast to the CCA2 game, identically. And we just skip the first phase. This is also the reason why the adversary is handed a challenge encapsulation together with the public information in the beginning of the game. Last but not least, beside the results regarding the realization of the secure message transfer of the secure channel, we also show how SBCPA can be compared to currently existing security notions for CAMs. However, due to different interface formulation of a general purpose CAM and an SB CAM, according security notions are rather incomparable. Therefore, we restrict the comparison only to security formulations of the more related tag-based CAMs. To this end, we have formulated the so far weaker CCA notion for tag-based CAMs, namely int given tag CCA security for tag CAMs. That is implied by all known relaxations of tag-based CAMs. We show that this security is not implied by SBCPA. Whereas on the other side, the SB security CPA is implied by int given tag CCA security for tag CAMs. In the end, I would like to clear out possible misunderstanding that might occur. Firstly, the SBCPA security is not a general purpose replacement for CCA2 security. SB security is meant to be used only when the encryption is combined with some form of authentication. In such cases, as argued in the beginning, CCA security and all of known relaxations are unnecessarily strong. Secondly, although in this work we give only constructions of SB CAMs in the standard model, the SBCPA theorems are not restricted to be used in standard model settings only. The CAMs in the random oracle model, for example, the currently to be standardized Kyber, are Fujisaki Okamoto transformation, and as such are already almost as efficient as their underlying one-way secure constructions. Similar observation can be done also with the React transformation. Whereas in the standard model, we were able to prove a straightforward simplification of an already quite practical, although maybe not comparatively efficient as in the random oracle model, existing lattice-based construction. Thank you very much.
We have time for questions. Rephrase this question. So you kind of showed that the various existing definitions implied this one, and that this doesn't say imply the other ones back. Is there any notion in which you can say this is really the minimum that's required for the applications you use, or could one always make it weaker? I don't know.
Nice question. We have managed, or Rebecca Schwert, one of the co-authors, have actually managed to prove that SBCPA security is in fact the minimal requirement. There cannot be a minimal weaker security definition in order to serialize a secure channel in conjunction with authenticated channels. However, this result concerns sender binding encryption, which is again a special form of public key encryption. Therefore, it didn't fit in this work. So you may find it in her dissertation of Rebecca Schwert. Yeah.
Thanks for the talk. So I was curious, how does your formalization of sender binding key encapsulation compares with some other formalizations of generalizations of KEM? So for example, there was something known as a split KEM, where you again have this distinction of a sender and a receiver. So there, I believe in a split KEM, when you do encap, then not only do you use the receiver's public key, but then you also use the sender's secret key. And then to decap, you use the receiver's secret key and the sender's public key. But in your sender binding KEM, I guess you are the sender you're using a sender's public key in some sense.
In some form. It's easier to think about sender binding KEMs as a special form of tag-based KEMs. So basically a sender identity can be seen as a very special form of a tag, and tag-based encryption requires to be secure for arbitrary tags. And there is the sender identities can be of many different forms, and it depends on which constructions you are used to prove them as BCCPA secure. You can do it directly, which we presented in our work. Another line of constructions would be constructing over the dual receiver encryption settings, where you have actually a sender encrypts twice, one with his own public key and the second time with the receiver's public key. And there is another property of soundness, which guarantees if the receiver is able to decrypt the ciphertext, then the sender is able to decrypt this in the same way, which basically provides then some form of plain text awareness. So there, the public keys are used as sender identities. In fact, regarding your question with the split KEMs and how they relate, I have to admit that I'm not aware of them. I didn't know about them, but it might be interesting to have a look inside. Thank you.
One more quick question. So you said you made construction from LWE and LPN, I believe. Did you look at any other starting assumptions or just chose those two?
You mean the pre-quantum factorization and so on?
Yeah, something like that.
Yeah, not yet, no. But it's obviously a open questions. One can maybe achieve much more efficient results with. One thing I have to say that is that we constrained ourselves to the standard model. And the constructions of LWE and LPN in the standard model are quite inefficient. So it was quite a good gain of efficiency when you're able to construct based on LPN and LWE. Maybe it's even more efficient with RSA.
Let's thank our speaker again. Next up, paper 55. This paper will be pattern matching in encrypted stream from inner product encryption. Our speaker will be Olivier Sanders.
Okay, does it work? Yes. Okay, thank you for the introduction. So today, end-to-end encryption has become extremely common. We indeed estimate that about 90% of internet traffic worldwide is encrypted, which is obviously a good point regarding privacy, but it also creates some security issues because it prevents any processing of this encrypted data. For example, if we want to detect malware using a tool such as Snort, this is not possible to do that directly on the encrypted stream. So it means that there is some kind of competition between privacy and functionality. So we have to choose between them. And in practice, privacy does not win because in most situations, what we see is a proxy that will act as a man in the middle that will decrypt the whole stream and then perform the processing directly on the clear data. So this questions the very point of end-to-end encryption. And so the question we want to solve is, can we do better than that? And in particular, in our paper, we focus specifically on the case of pattern matching, meaning that we want to search a specific pattern within a stream, because it's a task that we find in many services, such as intrusion detection system or content filtering. Here, I would like to stress that the problem of searching a pattern within a stream is very different to the one of searching a pattern within a database, because we have to, with the stream, we have to process the stream on the fly. We don't have the time to extract a set of keywords that will be associated to the data so as to enable efficient search. Moreover, if we look at some example, for example, of pattern that we search, we can see that they are not natural keywords or natural patterns. We might want to search any arbitrary patterns. So at first sight, it looks exactly like searchable encryption, because with searchable encryption, you can issue a trapdoor specific to a pattern and then use it to decide if a ciphertext is indeed an encryption of this pattern. But this is not exactly what we want to do, because what we want to do is to decide if the encrypted stream contains a specific pattern as a substring. So this is not exactly the same problem. And this is why, in practice, solutions based on searchable encryption use a technique that is called a sliding window method, which consists in setting a window of some fixed size and then encrypting the streams by shifting the window character per character, for example, as illustrated on the slide. So it works, but only for patterns that have exactly the same size as the window. Typically, if we look at the last pattern, it won't be detected this way. So we have essentially two solutions. Either we repeat the process for each possible pattern size, but it's clearly impractical, or we choose to split the patterns into smaller ones. Typically, we will choose the size of the smallest pattern, but here we are harming privacy. So this is not the solution we want. If we look at a very different cryptographic primitive, there is hidden vector encryption, which allows to encrypt vectors and also to generate secret keys associated with a vector K, which can contain characters, but also a specific character, which is called a wildcard, which is a character that matches every other character. And thanks to a test algorithm, we can decide if the vector K associated with a secret key matches the encrypted vector X. And the security property ensures that nothing beyond this, the output of this function will leak. So here again, it seems to be exactly what we want. But the problem is that the pattern can be contained anywhere in the stream. So it means that in practice, if you want to use hidden vector encryption, you will have to provide a secret key for each possible position. So for example, if you want to encrypt n bytes, you will have to provide n keys for a single pattern. So this has led to the design of a new primitive, which is called searchable encryption supporting pattern matching, SCPM, which can essentially be seen as an hidden vector encryption with key size independent of n. And there are only very few constructions that have been proposed, and they are rather complex. And in particular, they also do not achieve some important security properties, such as adaptive security. So in our paper, what we want to do is not to propose a new construction of SCPM, but rather we want to highlight some relation between SCPM and more popular cryptographic primitives. More specifically, what we will do in the first step is we will show a generic transformation from any hidden vector encryption to SCPM. And no such relation was known before our work. But as there are only few hidden vector encryption construction, we also want to to create a relation between SCPM and inner product encryption, for which the state of the art is huge. In this case, we already have something, because the PKC and Waters proposed 10 years ago a generic transformation from inner product encryption to hidden vector encryption, but this transformation doubles the ciphertext size. So we want to do better than that. So just a quick overlook of the first contribution. I will spend more time on the second one. So the idea we use is we notice that PKC et al. In a recent paper introduced a fragmentation approach, which consists in splitting the stream into several overlapping fragments, as illustrated on the slide. And they use this tool for their construction. But actually, what we notice is that this fragmentation is much more powerful than initially thought, because it guarantees actually that the pattern you are going to search is entirely contained in a single fragment. So it means that you can use an hidden vector encryption with the same key for encrypting each fragment, and then you only have to provide a set of secret keys for a single fragment and deal with the wildcard to deal with the offset within a single fragment. So concretely, what it means is that you have a pattern match, you have a system, a kind of hidden vector encryption with key size independent of the size of the stream. So it's exactly SCPM. So thanks to the fragmentation approach, we actually have a generic transformation from hidden vector encryption to SCPM. Now, if we look at the transformation from inner product encryption to hidden vector encryption, PKC Waters propose this transformation, which consists in doubling the size of the encrypted vector by adding some randomness R. And similarly, they increase the size of the vector associated to the secret key by adding some 1. And as you can see, the scheme is correct, because if X equal K, then you will have a 0 inner product. I have not described wildcards in this case, but the transformation really adapts to wildcards. And the opposite seems to be true. If we have a 0 inner product, the vectors then should be equal. But actually, this is only true for honest key queries. And unfortunately, the original paper does not contain a formal security proof for this transformation. To be fair, it was just an application of their work. It was not their core contribution. But the problem we have is that malicious queries can create some discrepancy between the inner product encryption experiment and the HVA one, because the adversary could leverage the randomness added to select some secret keys that do not match the challenge messages. So it's a valid query in the HVA experiment, but that yet lead to a 0 inner product. So it would be an invalid query for the inner product experiment. Fortunately, we show in our paper how we can deal with this issue by adapting the proof strategy. So my point here was not to say that there is a problem with this transformation, but simply to highlight these problems that will be much more difficult to solve in our second transformation. So our conversion actually moves the randomness added by PKC Waters into the secret keys. So it allows to add only one component to the initial vector. So it halves the size of the ciphertext compared to the PKC Waters transformation. And here again, we can easily check that if the vector are equals, then we will have a 0 inner product. And conversely, we have exactly the same situation. If the inner product is 0, we have equality of the vectors, but only for honest key queries. So we have to deal with malicious key queries. So in this case, we will consider differently two situations. For selective security, it's rather easy to manage such kind of queries. So we can prove selective security without any issue. The adaptive security case is actually much more complex, as I will explain. Because if we look at this transformation, what we have is that at some point the adversary makes some queries in the hidden vector experiment. And these queries are transformed by our reduction, which adds some randomness. And then the adversary receives the secret keys corresponding to K prime. And the problem is that each of these secret keys carry information about the randomness. So theoretically, an adversary could choose the challenge, the two challenges in such a way that none of the secret keys match these challenges. So it would be valid queries in the hidden vector experiment, but these challenges would yield different inner product, which will be considered invalid in the inner product experiment. So we have to rule out this situation to prove the security of our transformation. But just a few remarks. The first one is that if an adversary has the ability to recover the value K prime associated with a secret key, then it can trivially break the security of our system. So it means that the secret key must hide the vectors that it is associated with. So it looks like the notion of function privacy. But the problem with function privacy in a public key setting is that an adversary can always perform some exhaustive search to recover the value K prime. So it means that we cannot at best rely on the mean entropy of the pattern set. And so this means that this property depends on the context. And this is something we would like to avoid. Moreover, also the adversary cannot know the value, the vector K prime. It has some control over it because it selects the initial vector K, which is defined here. So this control must be modeled by our new property. So this leads to a new security notion for inner product encryption that we call key privacy, which is modeled as follows. So an adversary can make some key queries as usual, and at some point it will select a challenge vector Y and receive a secret key SKU for a vector U which is orthogonal to Y. And its goal will be to select a new vector, to find a new vector Z, which is orthogonal to U and which is not collinear to Y, because otherwise it can trivially win. So it's a very simple property, which is easy to assess for an inner product encryption schemes, but it is actually sufficient to prove adaptive security of our conversion, as we prove in the paper. So an important property is that, as you know, there is a computational goal. It does not depend on the mean entropy of the pattern set, and we show in our papers that this property is actually already achieved by many important construction of inner product encryption. For example, the construction proposed by Katsai and Waters, or the Okamoto-Takashima one, which achieves this property under the discrete logarithm assumption. We also show that some inner product encryption construction cannot achieve it. So for this scheme, we have to use the Katsai-Waters transform, which is less efficient. So in other words, what it means is that there are some inner product encryption schemes that are better suited to build hidden vector encryption than other ones. So to conclude, what we show in our paper is that we first show that we can generically build SCPM construction from any hidden vector encryption. We have a generic transform, the concrete transformation from hidden vector encryption to SCPM. We have also revisited the relation between hidden vector encryption and inner product encryption by introducing a more efficient conversion than the one proposed by Katsai and Waters. So as we explained, this conversion always achieve a selective security without any additional condition, but require some mild condition, which we call key privacy, to prove adaptive security. So it means that we can use actually any inner product encryption with satisfying this property to build a new SCPM construction. So typically, we will, thanks to that, we will be able to have adaptively secure SCPM proven under standard assumption and so on, because the state of the art of inner product encryption is huge. Okay, thank you.
We have time for questions. Maybe I'll start us off. On the, I think it was just the previous slide, you mentioned that you provide examples of schemes that do not achieve it. Were these examples kind of contrived examples just so that's not required, or were these natural examples?
There are actually real constructions that have already been published. Actually, there are constructions where the knowledge of the vectors associated to a secret key is necessary to perform the test operation. Because in some situation, if I can say, in some constructions, the secret keys consist of, for example, elements of the group G2 in a pairing setting. And so they implicitly hide the vector. But in some other situations, for example, constructions that are not based on pairings, to perform the test operation, you need to know the vectors, because they will be, the components of this vector will be involved as exponents in the computation. So such construction inherently rely on the knowledge of the vector associated to the secret key. And as I explained, if you know this vector, you can trivially break key privacy, because you just have to choose a vector orthogonal to public vectors. So.
Let's thank our speaker and all of the speakers in this session. I believe we're on to our next break. Enjoy a snack.